Hi, in this presentation I am going to provide my research on application of a new numerical approach for neural ordinary differential equations, and this presentation is intended for the 6th International Eurasian Conference on Science, Engineering and Technology. My name is Altan Onat and I am with the Eskişehir Technical University. So this is the outline of the presentation. First I'm going to give brief information about the neural ODEs. Then I'm going to present details of Fitzhugh-Nagomo model. And lastly, I'm going to explain the proposed numerical solvers and give the results and discussion. So I can say that a neural ODE represents the derivatives of hidden states using neural networks. Therefore, if you are trying to model a time series, you can construct continuous time dynamics model by using neural ODEs. It has been introduced by Chen et al. At 2018 in a NeurIPS conference, and it provides efficient memory usage and adaptive computation. However, the main problem or main challenge is the backpropagation through a numerical solver, and in the original paper it has been solved by the Pontryagin adjoint sensitivity method. And since then, neural ODEs neural ODEs are being used for physical systems, time series analysis, and generative modeling. In order to better understand the neural ODEs, we first need to look at residual networks. And it has been first proposed in the article given here. This is the figure of the residual networks. As you can see, the error between the xk plus 1 and xk is modeled by a function f. And in the residual networks, that function f is realized by a deep neural network. Therefore, I can say that the residual networks actually models the residual error between two consecutive time steps. And the difference of neural ordinary differential equations is it just models the differential equation instead of modeling the residual error between two consecutive steps. It tries to model the differential equation for that system. Therefore, the continuous time modeling with neural networks is made possible with the neural ODEs. And of course, a solution to such ODE can be found by this equation. Of course, if you have a nonlinear function or a function which cannot be analytically solved, then the integral term on the right hand side of the equation can be approximated by numerical solvers. And if you just substitute there the f of x times and time step, then it will correspond to Euler numerical solver for ODEs. And we can say that the Euler's method is the simplest one for the solution of the ordinary differential ordinary differential equations. Of course, we can use more accurate algorithms, more accurate numerical solvers, and second order Runge-Kutta is one of them. And if you look at from the perspective of residual networks, the second order Runge-Kutta can be modeled by this block diagram. As I have told you, the intention in neural ODEs is to create ordinary differential equation, and this is shown by dh of dht divided by dt, f of h dt, and theta t. Actually, our intention is to find the neural network parameters by using numerical solvers for the differential equation given here. Okay, so let me talk about Fitzhugh-Nagomo model. This is actually a simplified version of the Hodgkin-Huxley differential equation, and that those differential equations is being used to understand the activation of neurons. And I have considered the parameters given in this reference based on the current of 0.5, and the MATLAB's ODE 45 has been considered for the ground truth. You can understand that the MATLAB's ODE 45 is a pair of 5th and 4th order Runge-Kutta methods, and it is more accurate than the 4th order Runge-Kutta. This is the structure of the considered neural network for the neural ODE in this study, and I can say that the input layer just have 2 neurons, and output layer has just 2 neurons. This is being considered for modeling the Fitzhugh-Nagumo dynamic model. And we have 2 hidden layers having 32 neurons, and our intention is to solve this differential equation by considering the neural ODE structure, numerically solving the equation and then finding the parameters of the neural network. If I explain the numerical solvers used here, the conventional one is the TR-BDF2, which is trapezoidal rule with second order backward differentiation. And as well as that conventional numerical solver, I have considered improved one, which is given in this following article. I can say that these are the equations for the improved one, improved TR-BDF2 algorithm. So if we omit the first and third equations, second and fourth equations just corresponds to the conventional trapezoidal second order backward Euler differentiation formula. However, in the improved one, instead of directly using Fn plus gamma, we are just taking the average of those function evaluations. Actually, a similar approach is applied in the modified Euler's method. And we have seen in the previous reference that this approach provides promising results for the simulation of power electronic converters. This is the structure of the proposed numerical solvers. And I'm not going to explain the 4th order Runge-Kutta because you can find the details in the paper or in any fundamental numerical textbook. So these are the results of the neural ordinary differential equation. First, I have trained that neural network for 50 seconds of simulation, starting from the 0 initial state. And clearly, in this case, for this initial condition, the best results have been obtained by TR-BDF2. Of course, the error metric is mean absolute error in this case. And the second most accurate one is improved TR-BDF2. And Runge-Kutta is the last one. So in order to test the algorithm for another initial condition, I have applied the same approach. Just the initial condition is changed, and in this case, the most accurate one is the ITR-BDF2, which is the improved version of the TR-BDF2. And the second one is TR-BDF2, and again the last one is 4th order Runge-Kutta. As a conclusion, I can say that the application of TR-BDF2 or ITR-BDF2 can be considered in the training phase of those neural networks in the context of course, neural ODEs. And the conventional Runge-Kutta 4 is evaluated again for the Fitzhugh-Nagumo ordinary differential equation. We have seen that for the initial conditions I have considered, these two are providing the best performances, the proposed numerical solvers. And one of the significant advantage can be, even though it has not been tried in the article, the TR-BDF2 and ITR-BDF2 require only 3 function evaluations, whereas Runge-Kutta 4 requires 4 function evaluations. So actually TR-BDF2 and ITR-BDF2 are 2-step methods. However, since the solution in the neural ordinary differential equation case is a little bit different than the ordinary differential equation solution, because in the during solving the ordinary differential equations, we already or readily obtained the Fn. However, in TR-BDF2 and ITR-BDF2 usage, for the neural ODE solution, it is not readily available. Therefore, we need to first calculate the Fn. This increases the function evaluations by 1. However, still, those two algorithms requires 3 function evaluations. Thank you for listening. Any questions?